For part one of the 4.4 section video, we looked at solving exponential equations, and now we're going to switch to solving logarithmic equations. Now, one thing I want to make sure you are aware of is that you always need to check to make sure your answers do not make a zero or a negative inside the logarithm. So when I solve this, these cannot be a negative value or a zero. And if you think about that, the reason why is because if I take a number is any real number that is greater than 0 and not equal to 1 is my base, and I take that to any exponent. Okay, that could be a fraction, it could be a negative exponent, it could be a whole number, it could be a decimal. I will never get a negative result, and I will never get 0. If we take a look at our graph of a logarithm, you can see that that never happens. So therefore, we need to make sure that these values are not negative and not 0. But the same kind of principle exists as we were seeing before. If I have log base b of x is equal to log base b of y, the two values x and y must be equal to one another. So to solve these, we're going to look at our bases, make sure our bases are the same in the logarithm, and if they are the same and they are equal on both sides, then these components must be equal to one another. So 3a, we have log base 2 of 5x minus 1 is equal to log base 2 of 2x plus 17. The bases are the same, so therefore these expressions must be the same as well. So I have 5x minus 1 equals 2x plus 17. And when I solve this for x, I'm going to end up having 3x equals 18 when I move everything over, so x is equal to 6. Same thing over here, we have log of x minus 7 equals log of 5 minus x. Our bases are both equal because they're both 10. It's assumed in this one. And so our values x minus 7 has to be equal to 5 minus x. And so then when I solve for x in this case, I get 2x equals 12. So x equals 6. But when I take the 6 and I plug it into here, I get 6 minus 7 and 5 minus 6. And both of those are equal to negative 1, which I cannot take the log of that negative value. So therefore, these cannot work. Okay, there is no solution that can make this true. Okay, so you could state that there's no solution. The next bit is going to require us to be able to solve equations when we have a common variable in the denominator. I'm going to do a couple of practice without even using the logarithms yet, just to make sure we remember this process. First thing I'm going to do is multiply both sides by the denominator to cancel it on the left. So I end up getting 5 equals 2 times x minus 3. So then I'm going to distribute and get 5 equals 2x minus 6. And then I'm going to finish solving. I'll have 11 equals 2x, so x equals 11 halves. Over here, I'm going to do the same thing. Now something funky is going to happen because I'm still going to have an x on the other side. So I'm going to multiply both sides by my denominator to clear that out. So I cancel those, so I'm left with 3x minus 7 equals 10x plus 20. I'm just distributing as I go. I'm going to solve for x, so I'm going to move the x's to the right and the 20 over to the left. So I end up getting negative 27 equals 7x. So when I solve for x, I get x equals negative 27 over 7. Okay, so this process is going to help us in the next couple of questions. So same process is going to occur. So I end up having solve each equation log of 3x minus 4 minus the log of x plus 1 equals the log of 2. So remember, our quotient rule with our logarithms tells us that this subtraction can be rewritten as a single logarithm by doing division. So that's the same thing as having log of 3x minus 4 over x plus 1 is equal to log of 2. So that's something that we get from section 4.3. Once I've rewritten my logarithm that way, I have the same base. So This right here must be equal to 2. So I get 3x minus 4 over x plus 1 equals 2. So then I'm going to multiply both sides by x plus 1. So those cancel on the left. So I'm left with 3x minus 4 equals 2x plus 2. When I solve for x, I'm going to end up getting x is equal to 6. We're seeing a lot of x is equal to 6 on these problems. That's a coincidence, not something that you should always expect. Okay, same thing on this one right here. I have the natural log of x plus 3 plus the natural log of x is equal to the natural log of 10. Our product rule for our logarithms tells us if I have two logarithms with the same base that are added together, we can rewrite that as a product and combine it into one logarithm. So that's going to be the same thing as the natural log of x times x plus 3 is equal to the natural log of 10. So right now, I'm going to have that x squared plus 3x is going to be equal to 10 because they have the same base. So those two things, those two expressions must be equal to one another. I just distributed out the x. That's where I got x squared plus 3x equals 10. Now I'm going to solve this by subtracting 10 from both sides. So I have a quadratic. And then I'm going to factor this. So what two values add up to 3 and multiply to get negative 10? That's going to be 2 and 5. The 5 will be positive, and then 2 will be negative. And then, so our factors are going to be, those are our factors, so our values of x are going to be x is negative 5 and x equals 2. And then we're going to plug those in and check and make sure that I don't get any negative values or take logs of negative values. So if I plug in x equals negative 5 here and here, I end up getting logarithms of a negative value, which I cannot do. And so this answer is not possible. I didn't check the other one on part A, but it looks like 6 plus 1 is 7, that's positive. 3 times 6 is 18 minus 4, which is also positive. So this one is okay. This answer right here is okay. But here, that negative x equals negative 5 would give us negative values in our logarithm, and so therefore we cannot use that answer. But x equals 2 definitely does work. Next, we're going to look at examples where we only have a logarithm on one side of the equation. And so when that happens, we're actually going to convert this to exponential form. So let's see that with 5a. So here we have log base 5 of 3x plus 1 equals 2. So I only have a log on one side, so I'm going to rewrite this in exponential form. So that's going to be 5 to the second equals 3x plus 1. You can see right there that that's going to give us a nice easy equation to solve because 5 to the second is just 25 equals 3x plus 1. So 3x is going to be equal to 24. So then x will be equal to 8. Again, I want to make sure I don't get a negative value. 3 times 8 is 24 plus 1 is 25. So that is positive. Don't have to worry about that one. Okay, so then let's do the same thing. First, I want to condense this down. So I'm going to end up getting log of 3x plus 6 over x minus 2. We're condensing that logarithm based on our rules that we saw in 4.3. Now I have a log on one side, so I'm going to rewrite this in exponential form. That's going to give me 3 to the second equals x plus 6 over x minus 2. So that's 9 equals x plus 6 over x minus 2. And then you're going to use the same properties that we saw earlier to solve this when you have a variable in the denominator. When you do all that side work, which I've just done quickly over here, you end up getting that x is equal to 3. Okay, same thing over here. First, I'm going to actually divide both sides by 4, so I get the natural log of 3x equals 2. And so now I have a log on one side. My base is e, so I'm going to rewrite that as an exponential function. So I get e to the second equals 3x. Then I'm going to divide by 3 on both sides. And on this one, I'm definitely going to have to round my answer. And we end up getting 2.463, which rounds to 2.46. Again, that's approximate. That's our answer for that one. Again, we're going to combine these, so I end up having log of x times x minus 3 equals 1. So rewriting that, I get 10 to the 1 equals x squared minus 3x. That looks very familiar. So then 10 to the 1 is just 10. I'm going to move that over to the other side. So I end up getting x squared minus 3x minus 10 equals 0. Factors to x minus 5 times x plus 2. Therefore, my values of x are going to be equal to positive 5 and negative 2. But I want to make sure I don't end up with any negative values. Negative 2 would give me taking logs of negative values, so that one will not work. My solution is x equals 5. That's it for part 2. We have one more video, part 3, on section 4.4. Please make sure you watch the entire thing.